Good afternoon. My name is Matt Heidebrecht. I'm with Courtney Mort, Jordan Pontillo, and Scott Strachan. This video is for our final project, EENG 307 Feedback Control Systems. For the project, we are required to pick and implement a control and plant feedback system with some sort of social justice rationale. The system we chose is a bandpass filter with application in a hearing aid. A bandpass filter will amplify a certain range of input frequencies and dampen out all the other frequencies. Our goal was to amplify frequencies between 4 and 8 kHz because that is a common hearing loss frequency range, and the most prominent frequencies in the human voice are between 3 and 5 kHz. To start, we used a common bandpass filter as our plant. Our general design is the one pictured. The input is Vn coming as a sine wave, and the output is the voltage across the resistor load. The resistor load would be the speaker and the hearing aid. The transfer function for the system Vn to the voltage across the resistor is pictured at the bottom of the screen. Specific values for the capacitors and inductors have not been selected at this point. We need to analyze how the different components affect the plant response. As a starting point, we used values derived from equations pictured for our specific plant. F1 and F2 are the high and low frequencies that are to be passed. Our plant values have been labeled to correspond to these equations. From these starting values, we discovered through manipulation that L2 changes the bandwidth, L1 moves the bandwidth through the frequency spectrum, and C1 changes the dampening response. Courtney will now be talking in more depth about the analysis of the plant and our final plant values.
Hey, this is Courtney Mort. As Matt said previously, our values were to be determined by website resource. However, these bandpass filters were not designed to be used in conjunction with a controller as the project specifies. Therefore, after playing around with values, in order to get the response we're looking for, we came to these approximate orders of magnitude for each component. As you can see, the bandwidth shown on the magnitude plot is longer than the selective range we're aiming for. It goes from about 1,000 radians per second to 20,000 radians per second, or 160 Hz to 3 kHz. There is also a sharp peak happening at about 130 Hz due to the capacitance chosen. Scott will speak a little later on how we attempted to compensate for these with a controller. Here is the Nyquist plot for our system. The big figure 8 loops are largely due to the capacitor's resonance spike. At this order of magnitude, it is hard to see whether or not our plant is stable. Zooming closer, we see there are no encirclements of the point -1, 0. Thus, we can see the plant is stable on its own. There are no right half plane poles, and there are no encirclements of -1, 0. Therefore, according to the Nyquist stability criteria, the plant is stable. It is unlikely that an outside source will disturb the plant due to the cutoff frequencies eliminating signals outside of the range. A signal at exactly 130 Hz, the region of our capacitive spike, might have some slight interference, but not enough to warrant action at this point. We have decided that the reference input should be a sinusoidal wave to simulate a sound wave. Next, Scott will discuss our design specifications and our controller system.
The design specifications for this project were chosen to create a stable, pleasant experience for the end user. Our steady-state specification was to amplify any sinusoidal inputs within the passband of the filter while attenuating all other frequencies. Because stability was an important consideration for this system, our other two design specifications involve gain and phase margins. The goal with these design specifications is to increase the stability of the system as much as possible to improve the user's experience. To quantify these design specifications, the steady-state gain of the system should be minimized for all frequencies less than 4 kHz and all frequencies more than 8 kHz, while providing a non-zero gain between 4 and 8 kHz. For a gain margin, we were aiming for at least 40 decibels, and for a phase margin, we were aiming for at least 35 degrees. To achieve these design specifications, we implemented a lead-lag controller. This kind of controller allowed us to reduce the resonance that we saw earlier with the use of zeros, while amplifying any signal within the passband with the use of poles. Here you can see the controller function that we developed using SisoTool in MATLAB. It may look intimidating, but it came from some fairly straightforward manipulation of the plant transfer function in SisoTool. Here we can see the final root locus and Bodhi plots for the final system with the controller implemented. While developing the controller, we focused mainly on the Bodhi plot. The first step was to place a pair of complex zeros at the resonant frequency. This accomplished two things. The first was that it decreased the amount of resonance seen in the system. The second thing that this does is increase the slope of the magnitude Bodhi plot, which further attenuates any signals below our 4 kHz threshold. The next step was to use a pair of complex poles to effectively undo the slope increase created by the zeros and give us a flat magnitude plot across our passband. Finally, we placed another set of complex poles at the end of our passband to attenuate any signals at frequencies greater than our 8 kHz thresholds. Now that the controller is implemented, we can check to see if we've achieved our design requirements. By looking at the magnitude Bodhi plot, we can see that the system provides a constant gain across our desired frequencies and that everything else is attenuated. Checking for the gain margin, we can look at the phase plot and see where it crosses over minus 180 degrees. Looking up, we see that the magnitude is at about minus 140 dB, giving a gain margin of 140 dB, which is above our goal of 40 dB. By looking at the magnitude plot, we can see that it never crosses over 0 dB, meaning that we don't have a crossover frequency. This gives us an infinite gain margin. As mentioned before, the gain margin was 140 dB and the phase margin was infinite. Finally, the plant is bounded input, bounded output stable. Now Jordan will continue the analysis of the system.
This plot shows the poles and zeros of the open loop transfer function. There are 3 poles, though only 2 are shown on this plot. Those 2 are an imaginary pair centered at 0. The other pole is a real value at negative 9.9 times 10 to the 6th. 3 zeros are also pictured, an imaginary pair centered at negative 0.21 and a 0 at 0. This is the closed loop system. Initially, a sinusoidal function is the input, which then travels through the gain block, which had to be very large in order to achieve a visible output. Our specific controller is the compensator and was explained by Scott. In order to verify our bandpass filter rejects and accepts the correct range of frequencies, we ran a variety of sinusoidal waves through the loop. At an output of 4,000 Hz, which is within the frequencies that should be passed, a signal is obtained. At frequencies both below and above our range, the signal is obtained as shown in the other graphs. In this case, no signal. Ultimately, we reached several conclusions. Firstly, we met all of our design criteria. The system passes all of the frequencies in our range and eliminates signals outside of that. The gain and phase margins are at acceptable levels per our goal. The system is also stable on its own, and we determined all of these using MATLAB and SisoTool. We got some unrealistic results. To begin, the capacitor used in our design is unrealistic. Most capacitors are on the scale of micro to pico. Additionally, the gain margin is somewhat unreasonable at 140 decibels or 10 to the 7th. Our controller is additionally unreasonable due to being very complicated since it was designed in SisoTool. It would likely be extremely expensive to implement and design. From this information, I hope you have a clear understanding of bandpass filters and the necessary controls that have been achieved. Thank you for your attention.